Hi everybody, welcome to the next lecture on video coding, this time about transforms, the KLT and the DCT. So first about optimum transforms, or particularly the KLT, and we will see in a moment what that is. So previously we chose a DCT, the discrete cosine transform, or rather the two-dimensional DCT, where we multiply a DCT transform matrix from both sides as a transform matrix. But the next question is, how do we choose a suitable or optimum transform matrix out of the many possible? So we saw there are many types of DCT, and why does it have to be the DCT and not something else? So this is what we want to answer today. The ultimate goal of a video coder is to save bits. So we would like to have a transform matrix which leads to a minimized number of bits for describing or coding an image. In a complete coder, we apply irrelevance reduction, the properties of the eye, and redundancy reduction, the properties of the source. Since this becomes somewhat difficult to solve for a simple transform matrix, we simplify our problem by looking at the properties of the source only, meaning the redundancy reduction, or only lossless coding. To minimize the needed bits for the lossless case is still mathematically a hard problem. So basically we have a tough problem to solve. So what do we do as engineers if the problem is too tough? We simplify the problem, right? Basically turn into a problem which is similar but solvable. So it's better to solve a similar but simpler problem but have no solution at all, right? So hence we reformulate our problem. We would like the subband signals to be statistically independent of each other, which means no mutual information. So if they would have mutual information, that would be a waste of bits. Basically, we would encode the same information several times, which we don't want. Right, so this is already a good formulation for lossless compression. Yeah, so actually this approach of simplifying a problem in general is a good approach in engineering. So statistical independence of the signals x and y here means the probability of p of x. So x is our signal, and x here represents some sample, and then this p of x is the probability of the sample. And we want this probability p of x to be the same as this probability conditioned on the other signal, right? The other signal y. So we want to have the probability depending on x alone to be the same as the probability of x given the knowledge of y. So this means x contains no information about y, or vice versa, y contains no information about x, right? So the additional knowledge of y doesn't give us any additional information of what x might be. And this is what we want to have. So this is what we actually want to avoid, additional redundancies in our transmitted signal to transmit information only once. So independence leads to uncorrelatedness, meaning the correlation between x and y is zero. But uncorrelatedness in itself leads not necessarily to independence. This is only true for Gaussian distributed signals. So this can actually be shown in probability theory, but this is a restriction. So I mention uncorrelatedness because that's something we can easily compute, right? So if we have two signals x and y, we just compute the cross correlation, and if the cross correlation is zero, then we know there's no correlation. But we know that this is not sufficient, right? So this is only sufficient if we have a Gaussian distribution, which usually we don't. So we obtain Gaussian signals, for instance, if we add up many more or less random signals. This is the law of large numbers, or the central limit theorem. So if we have many random distributions and we add them all up, say many throws of a dice, then it becomes closer and closer to a Gaussian distribution. So this statistical independence is again hard, and hence we choose the easier to obtain uncorrelatedness anyway between the different subbands. So we know that the subbands are likely not really Gaussian distributed, but still uncorrelatedness is so much easier to compute than independence, that again we simplify our problem. So we simplify it in the way that we say, maybe it's close enough to a Gaussian distribution, and then we can take uncorrelatedness. So now we make the assumption here that the probability distributions of the subbands are Gaussian, or at least very close enough to a Gaussian distribution. So again, this is something we need to keep in mind, right? That our solution that we now will be getting is relying on this assumption of Gaussian distributions, which is more or less realistic or not. So we again reformulate our goal that we would like to have subbands yk of m. So m was the block index, k was the subband index here, and y was our subband sample for subband k and block index m. So we want to have those subbands, each being a different sequence of samples, to be uncorrelated to each other. So the different subbands should be uncorrelated, right? So we take this in formulation instead of getting the lowest number of bits, because that's easier to solve. So that means that the expectation of the two signals yk of m and yl of m, the product and the expectation of it should be 0 for any k unequals l. So k and l are different subband indices. Right, so this is basically the definition of the cross correlation. So the cross correlation of those two should be 0. Yeah, so this is a correlation between two subbands, and here we only consider the correlation lag 0, right? So when you look at the cross correlation, then usually you have a sequence. So you have cross correlation of some additional index, say n, and then you have the shift m minus n here in one of those entries. Here we don't have it. So this is another simplification. We don't really take the entire correlation. We just take the correlation, the cross correlation, at time lag 0. So here, this is another simplification. So we are getting further and further from our original requirement of having the least amount of bits. But at least this way we get a solution. Yeah, so this means different subbands shall be uncorrelated for this time lag 0, meaning each subband should carry new information. So keep in mind all those simplifications. So the solution should be taken with a grain of salt in this way, because there are a lot of assumptions in it. So also this would mean we might have no correlation for lag 0 if they are aligned, but we might get correlation if we have a lag. Right, and that means there might be still common information hidden in the subbands. Yeah. So in this way we can argue that we have minimized redundancy between the subbands in some respect for Gaussian signals and for time lag 0 to obtain some sort of information separation between the subbands. In this way we have made this problem mathematically more tractable. So now we basically have simplified our problem formulation such that we can obtain a mathematical closed form solution. But keep in mind this solution is not for the original problem, so that's why this in the end is not the only solution, but it is a simple solution. Yeah, first assume a one-dimensional signal x, like an audio signal or the rows of an image, to simplify our notation. This signal is again divided into blocks of length n, obtaining blocks bold x of m with a block index m, and then each block is transformed using our transform matrix T. So again, here I also took this simplification approach. Instead of dealing with two-dimensional signals right away, I'm taking the simpler case of one-dimensional signals first. Right. And this works particularly if we have separable signals, which really can be decomposed in rows times matrices, which again for images might or might not be true. So the solution we will be getting is, again, this is another simplification. We will get the optimum transform for rows and later columns, but this is not necessarily the same as a transform for both together. Yeah, but again, it simplifies the solution. So now we have this formulation for one-dimensional signals. So we have a signal block x, we multiply it by this transform matrix T from the right-hand side, and the result is our vector y for block m. So here is an example of x. So x is now containing our blocks. So here in the first row you see the first block, in the second row you see the second block, and so on. So here you can see the block index, and the block index goes up as we go down. And then the result will be blocks y. So first block in the first row, next block in the second row, and so on. So x and y are matrices of size L times n. So n is horizontally the number of columns. It's basically the transform size, and L is the number of blocks in the signal. Yeah, so with our transform equation, this simply becomes y equals x times t. Simple enough. So now we have a quite compact mathematical description. So the columns of the matrix Y contain the signals of the different subbands. So the first column is for instance, the lowest frequencies, the next column is the next higher frequencies, and so on. Right? So one column is one subband, first column is subband k equals 0, second column subband k equals 1. So vertically we have the subband view. So each column is one subband. We would like to compute the correlations between the different subbands, again at time lag 0 to simplify matters. So to obtain a transform matrix where this will be 0, right? So basically we want to optimize now our T, the transform matrix T, such that the correlations for lag 0 of the different subbands will be 0. So how do we obtain the correlations? How do we obtain the correlation matrix? We now obtain the correlation matrix of the subbands by multiplying the different subband column vectors. Column vector of subband k equals 0 with itself results in its signal power. Product of subband k equals 0 with k equals 1 results in their cross correlation with lag 0. If you multiply the transpose with the matrix, in this way each subband column becomes now a row from the left, which we then multiply with each subband column on the right. So this is how we would compute the cross correlations of the subbands. So we would simply take our matrix Y, the result with our multiplication with the transform matrix T, and take the transpose version of it and multiply it from the left hand side. So here you can see Y. So the first column, for instance, is the first subband. If we transpose it, then the first subband becomes this first row. Right, so here's subband number 0 in the first row. Here it is in the first column. And if we multiply those two matrices, we have the first column times the first row from the left results in the entry on the upper left-hand corner of the result matrix. Right, and in this case, we just square each entry. So each sample squared, and then we sum them up. That's the result of the first upper left-hand entry of the result matrix. And if we sum the squares of the samples, it's simply the signal power. Right. Then for the next lower entry, so the entry on the second row, the first entry of the second row of the result matrix consists of taking this first row on the right-hand matrix and multiplying it with the second row on the left-hand matrix. So the second row is the next subband samples. So we now multiply the samples of the first subband with the next subband, and that's the cross correlation with lag 0. Right? So the next entry will be the cross correlation, and this is what we actually want to have. So in the end, if all the cross correlations shall be 0, then all the off-diagonal elements of the result matrix AYY should be 0. The diagonal elements all contain the powers of the subbands, and the off-diagonal elements contain the cross correlations, which we would like to be 0. Right. So this is now our optimization goal. We have AYY as Y transpose times Y, and we want this to be a diagonal matrix. So here each element AYY consists of this cross correlation with lag 0. Right? We take channel number I, or subband number I, subband number J, and we multiply the two. So if I is equal J, then we get the power. If I is not equal J, then we get the cross correlation. Yeah, so this also means that AYY is now an n times n matrix, so exactly the size of our transform matrix, which now contains the autocorrelation and cross correlations. So we have the autocorrelations on the diagonals and the cross correlations on the off diagonals, each with lag 0. On the resulting matrix AYY, each diagonal element contains the power of the corresponding subband, and the off-diagonal elements contains the cross correlation of the corresponding subbands, which we want to be 0. So this is what we would like to have, right? To obtain our goal of uncorrelated subbands, this correlation matrix needs to be a diagonal matrix of this form here. So everything is 0 except for these diagonal elements which contain the power, which I here call sigma squared. Yeah, so now we have a formulation for our optimization. Basically, this is the target. This is what we want to achieve. And we now want to find a T which achieves this form, right? Because if we have such a transform T which decorrelates the subbands, then we have something like no information leak from one subband to the other, at least under our assumptions. So we need to find a solution which satisfies this goal, this target here. We stack our signal into the size L times n, matrix X as above. So we take this X, we compute the Y with this T, the still unknown T, and then we compute Y, AYY. Right, so AYY is Y transpose Y, then we plug in this Y here. So we have X times T, transpose times X times T, and if we transpose a product, we apply the transpose to each of the product's factors, and then switch the order. So we have then T transpose X transpose. This is what we see here. So here we have T transpose X transpose times X times T. right? And we have this expression x transpose times x in the middle, and this is the autocorrelation matrix of our signal blocks in the signal x. We call this AXX. So this simply results from x transpose x, which is now the autocorrelation and also the cross correlations of the different blocks. Yeah. So remember, the autocorrelation function of any signal x is defined by this formula here. In general, we have some shift n here, and we basically only consider the case where we have no shift, lag 0. Yeah, and the cross correlation between two signals x and y is defined by this equation here, x times y, again with a shift. And for lag n equals 0, this corresponds to the usual vector multiplication that we used here. Yeah, so observe that x contains the blocks of the signal x, which here we assume to be one-dimensional for simplicity. Each row is one block of our one-dimensional signal, for instance, a block of a line of our image. So we take snippets of our rows of our image and put those snippets into this matrix X, one on top of each other. Right, so this means that each column of this X corresponds to one position in each block over the block index m. So in effect, this is a downsampled signal x along each column of matrix X, where each column corresponds to a different phase instead of a different subband of the downsampled signal. So if you take those snippets and put one snippet in each row, then if you look at the columns, then the columns, say the first column, then contains always the first entry of each of those snippets or each of those blocks, right? And in effect, we look at a downsampled sequence, and this downsampled factor is given by the size of those snippets or those blocks. And then the position is the offset for this downsampling, which we call phase. So if we have the first column, we always have the first entry for each block. If we take the second column, we always have the second entry of each block, and so on. So it's basically different phases of the downsampled signal. So depending on which way you look, horizontally along the rows you have the blocks, and vertically along the columns you have the downsampled signal, downsampled with different phase offsets. Yeah, so this means the correlation matrix AXX corresponds to the correlations of the different downsampled versions of X. And usually there will be a lot of correlation, right? So if you shift the signal a little bit, it still has a lot of correlations. So remember that our goal was to make AYY a diagonal matrix, which is equivalent to the subband signals being uncorrelated. So now we have AYY equals T transpose times AXX times T. Right? Remember, now we take AXX as our X transpose times X. This is the correlation of the different phases in our signal. And now we want to find T such that AYY becomes this diagonal matrix. So how do we do that? So given matrix AXX, we need to determine the transform matrix T such that AYY becomes a diagonal matrix. The advantage now is that AXX is much smaller than X. Right? If we have many samples, then X might be a tall matrix, but AXX is an n times n matrix. Yeah, so it has a finite dimension, it is quadratic with dimension n times n, and hence we can easily find a solution. Well, relatively easily. So now we can see that if we only had one transform matrix from just one side, we would only need to be it would only need to be the inverse of AXX in order to get a diagonal matrix, since we would obtain the identity matrix, which is also the diagonal matrix. So imagine we wouldn't have this T transpose, right? Then we would just need to multiply both sides with AXX inverse. Then we would have AXX inverse. That would determine the T, right? So AYY would we would plug in some diagonal, and then we would obtain T by just taking the inverse. Yeah, but we don't have that, right? Yeah, but we have the transform from both sides, so that doesn't work. So let's take a look at the eigenvectors of AXX. An eigenvector has the property that a multiplication of it with a matrix results in the same vector, but multiplied with an eigenvalue. So this is what you know from linear algebra. You have eigenvectors. Each matrix has eigenvectors, and the eigenvector has the property that if you take the matrix, the corresponding matrix, and multiply it with this eigenvector here, this is a column vector here, then we obtain the same vector but scaled by a scalar lambda 0 or lambda naught. Right? So basically it turns this more or less complicated operation of a vector times a matrix into a simple operation of a scalar times a vector. Right? And it turns out that a matrix of dimension n by n has exactly capital N eigenvectors and eigenvalues. So E naught is called the eigenvector, lambda naught is called the eigenvalue. Yeah, and also since our matrix is symmetric, the eigenvectors are also orthogonal to each other, meaning Ej times Ek transpose is 0 if j is not equal k. And if we multiply Ei times Ei transpose, so the vector with itself, we get 1. So we get the length of each vector is 1. So that's convenient because this means we have a new coordinate system basically in this way. So hence we can construct our transform matrix T as having all eigenvectors Ek of AXX as its columns. So this is now our trick. So T now simply becomes a collection of our eigenvectors. Right? Each column is one eigenvector because we know if you multiply the eigenvector with AXX, then it's again this eigenvector. And since those eigenvectors are orthogonal to each other, we can just take then this result and multiply it with those eigenvectors from the left-hand side, and we will get we get a diagonal matrix. So this is the important step here. So this means that if you multiply this matrix from the right-hand side onto AXX, we obtain the same eigenvectors but multiplied with the eigenvalues lambda k. Right? So this is the result. We take AXX, of which these are the eigenvectors, multiplied by T, which consists of this collection of eigenvectors, and the result is again this collection of eigenvectors but now scaled with the eigenvalues. Right? So each column is still the eigenvector but now scaled. Right? So we just use this identity here. Yeah, and the important property is now that the Ej are orthogonal to each other, and all what is left after the multiplication from the left-hand side with T transpose, which now has the eigenvectors in the rows, is a diagonal matrix. Because only if you multiply a vector with itself, we get a value of 1. If you multiply one eigenvector with another eigenvector, the result will be 0. Right? So this is then the result. So here we are using aj times lambda j times ej is lambda j, and if we have different indices here, different eigenvectors, then it disappears to 0. Right, so what we have here, here are the different eigenvectors multiplied with each other. They all become 0, and only the identical eigenvectors multiplied with each other become factor 1. So all what's left is this eigenvalue here. And this is exactly the form that we want to have, right? So now we found the solution. We have axx times t consisting of the eigenvectors in the columns. From the left-hand side, we multiply with t transpose, where the eigenvectors now appear in the rows, and the result is this diagonal matrix with the eigenvalues on the diagonal. And remember, this is AYY, and then that means the eigenvalues are the powers of each subband. Right? Now those eigenvectors represent the powers in each subband, or the energy. So observe that here we indeed achieved our goal of a diagonal matrix as AYY for the uncorrelatedness of the subbands, at least uncorrelated for lag 0, using T as a set of eigenvectors of axx. So this is actually now a neat and simple closed form solution for this simplified case. Yeah, so in conclusion, for one-dimensional signals with a matrix of signal blocks X, the decorrelating transform is T, and the uncorrelated subbands are obtained with Y equals X times T. Right, so this is the T that we just obtained. This means we now reach our goal of diagonalizing our cross-correlation matrix, AYY, with a transform matrix which consists of the eigenvectors of the autocorrelation matrix AXX in its columns. And this is now the so-called Karhunen-Loeve Transform, or short KLT. Right. Also see, for instance, this link here. And this is also called Principal Component Analysis, or PCA, or also Hotelling Transform. So depending on which area, people came to similar conclusions and gave it different names. But it's basically all the same. Yeah, so in this way we obtain one KLT matrix for the rows of our picture and one KLT matrix for the columns. Hence, two KLT matrices for the entire picture. So remember, this came from our assumption that we apply it one-dimensional separately for the rows and the columns. And this is good if we have a separable signal, but images are usually not separable signals. So that's another reason why the KLT might not be the optimum for images. But in any case, we have a neat solution which we can apply now. Yeah, but we need one KLT for the rows and one for the columns. The KLT for the rows is obtained by assembling all the rows of all blocks of our picture in a picture or set of pictures into a matrix X. So these are the snippets, right? Snippets or blocks of our picture. They are all collected and put into this matrix X. For instance, if we have blocks of size 8, we would go along each row and take snippets or blocks of size 8 pixels and put each of those into the matrix X, one after the other. And then we use it to compute the correlation matrix AXX and then compute the eigenvectors to obtain the KLT as a set of these eigenvectors. And similar, the KLT for the columns is obtained by assembling our columns of all blocks into this matrix X. Yeah, the problem with this KLT is that it doesn't have a fast implementation like a DCT, which can be implemented via an FFT, a fast Fourier transform. Also, if you want to have the optimal KLT for our image or a set of images, we would have to calculate it first and then transmit it as side information to the decoder, which would increase the necessary bitrate. So remember, the decoder also have to know which KLT we used to be able to invert it. This has the consequence that it is usually only a theoretical construct, but not really used in practical coders. Right? So basically we can use the KLT to see how good our transform is as a comparison. Observe that for the construction of the KLT we need useful, reliable statistics and hence many blocks to compute our correlation matrix AXX from. Hence we need to compute the correlation matrix from all blocks of an image, or even better, from all blocks of a collection of images or a video. So we take, for instance, if we have a video, we would take all frames and put them together in our matrix X, which would then be a really tall matrix. Right? And we would need to do it for the rows and the columns. Although usually the KLT for rows and columns should be very similar for natural images. So there should only be slight differences. So here's a little Python example for audio, again for simplicity because it's already one-dimensional. So we take a one-dimensional signal like an audio signal and we take a stereo recording with two different sources mixed together using panning. So we have amplitude-based mixing and no delays. So we just take two audio signals and assume those audio signals are two different subbands, for instance. The original stereo mix has the following mutual probability distribution. Each axis is the amplitude value of one of the stereo values, stereo channels. So amplitude means the sample value. Each pair of samples of the two channels is a dot in the plot. Hence, strictly speaking, it is a scatter plot and only becomes a probability after normalization such that the integral over it becomes 1. So here this is a scatter plot. And here we can now easily see the correlation between the two. So horizontally, we have the amplitude of channel 2, which is the sample value. And vertically, we have the amplitude of channel 1, again, the sample value of channel 1. And you can see there's a lot of similarity. So when we have a stereo recording, say we have two microphones at the same position, which are directed in different directions, then two sources or one source will give you just slightly different amplitudes on the two microphones, but they still will be very similar. And this is what we see here, right? So this is also true if we have two sources. So imagine we have two microphones at the same position, directed slightly different, and we have two speakers in front of them. Then we have a slightly different mix for each of those two microphones, right? So, but each microphone contains both sources. So each microphone is now one channel, and we want to see what we can do, what can happen if we decorrelate the two. So this similarity can be seen here in this diagonal shape. So if we would have the two channels identical, we would have a straight line, right? That would mean channel 1 identical to channel 2. But here we have almost a straight line, we have more like an ellipsis. That means the two values are only slightly different. So this similarity, the correlation of the two channels can be seen in the diagonal shape of the distribution. And we would get something similar if we would apply a transform matrix to blocks of size 2 of an image, right? Because samples of neighboring samples of an image are also usually very similar. So we would get some shape like this. So we can now apply the KLT, the Karhunen-Loeve Transform, to the two channels of our mix and obtain a 2x2 KLT matrix. Each pair of samples is multiplied then with a 2x2 KLT matrix. So here one pair of samples means one sample from microphone 1 and one sample from microphone 2. Yeah, and then we obtain new channel signals which are uncorrelated between the two channels. So the resulting mutual PDF can be seen in the following plot. So this is after KLT. So here you can see the KLT now acted like a rotation matrix. So remember, when we have two dimensions, then we have vectors of size 2. So each block basically is having two samples, which we just plotted. And if we apply a rotation matrix, which consists of cosine, sine, minus sine, cosine of the angle that we rotate, that basically implements a coordinate rotation. And this is basically what we observe now. This looks pretty much like a rotation of the original. So we take this shape here, this elliptic shape, and now it appears aligned with the two axes. So this same shape instead of diagonal now is aligned with the x and the y axis. Right. So, and this alignment to the axis is what we would expect if the two signals are uncorrelated. Right. So this looks pretty much like a separable function where we have the two-dimensional function consists of function of axis 1 times functions of axis 2. Right? So each does its own thing and is not really bothered by the other one. At least it looks like this, right? At first glance. So when you look more closely, it's not quite. Here you can see slight deviations from the symmetry here. So it's not exactly independent. It's uncorrelated, but it's not really independent. So we see the PDF is rotated such that its axes are now aligned with the axis of the plot, which is a sign of uncorrelatedness. So it's indeed uncorrelated. But now the two channels have very different amplitudes or power. So what will we see if we make these powers of the two channels equal by normalizing them to 1? Right. So here you can now see channel 2 has a lot of power, channel 1 has only very little power. So very unequal. And imagine we have our two signals. Originally, we assume those two signals are very similar, which we saw in this diagram. So having one channel much weaker than the other is kind of not very natural. So we normalize them such that each has the same power. So we do this by dividing the KLT subbands by the square roots of their eigenvalues, which are the powers of the subbands. So remember, the eigenvalues are the powers, and if we take the square root, we get the voltages or currents, or basically the signals. It's a signal domain itself. So this is called whitening and can be seen in this plot. So here, this is the result after whitening. So here we normalized the two outputs to have the same power. And here you can see, indeed, we now have the same power on each. And now you can also see that this is not really aligned with the two axes. So again, we get this diagonal shape here. It looks almost like we have this underlying square which appears here all of a sudden. And the square here is again having this diagonal shape. And that means we have similarities between those two channels. Right? So whitening now made it obvious that we are not independent. So we achieved uncorrelatedness, but not independence. And if we would have a Gaussian distribution, then this would be actually a circle, right? And that's also why if we have a circle, then it doesn't matter if we have uncorrelatedness or independence, then both would be the same. But here we can see, since this is not a circle, we can see structures which are diagonal. And that means we need a second step. Right? After this whitening, since it's not Gaussian, we need a second step, which actually rotates the whitened version such that we have this alignment with the two axes again, so that we get a separable signal. So now we can recognize that there are still diagonal structures. This means there are still dependencies between the two channels that we obtain. Observe the differences between correlation and dependencies, right? So this leads us to the so-called independent component analysis, ICA. It again rotates the mutual PDF now for the whitened channels, the normalized powers, such that its structures are now aligned with the plot axis. And this uses a rotation matrix here, which I just mentioned, this cosine, sine, minus sine, cosine of some angle alpha, and it finds the suitable rotation angle alpha such that we obtain this rotation. The rotation that aligns with the axis. Yeah, and we choose the angle for the two channels which maximizes the non-Gaussianity of the two resulting channels, or the entropy differences, making channels as different as possible, or the kurtosis, the fourth moment of the resulting channel signals. So we have different choices, and that's up to us. And we take those measures because we need to have a mathematical formulation for this alignment. Right? It's not like that our algorithm can take a look at it. Right? This is a picture which our eyes can see, but our algorithm just needs to have a function which computes numbers. And if we rotate this, then those two channels will get different mutual information. And if we align them, if we align those structures with the two channels, we minimize the mutual information between the two channels. And minimizing mutual information can also be expressed by maximizing non-Gaussianity. Remember that if we add two random signals, it becomes more similar to a Gaussian distribution. So that means if we have two signals which are not added together, then it's more different from a Gaussian distribution, so it's more non-Gaussian. So that's why we want to maximize the non-Gaussianity. Another way of expressing is that we want to take the entropies of the two and maximize the entropy differences between the two. Or we want to take a look at the probability distribution, and instead of maximizing considering the non-Gaussianity explicitly, we look at the kurtosis. This is the fourth moment of this distribution, of the probability distribution, and this is another measure of the non-Gaussianity, right? So if you maximize the kurtosis, then this maximizes the non-Gaussianity. Yeah, so these are different information theoretic measures which are relatively easy to compute. And we can take the one which is easiest to compute for our choice. Right. So here you can also read more in this link about independent component analysis. So yeah, this is where we have a little bit more information theory in it. So if you are familiar with information theory, that's easy. If not, this might be incentive to look into information theory. So the first criteria is based on the observation that a sum of random samples becomes more Gaussian in normal distribution than the original samples, which I just said, the central limit theorem tells us. So hence the original samples must be less Gaussian, and this can also be seen as minimizing the mutual information. So here you have links where you can read more about the central limit theorem and more about the mutual information as part of the information theory. Yeah, the mutual information or the similarity to a Gaussian PDF can also be measured by the so-called Kullback-Leibler divergence. So this is usually easier to compute than directly the mutual information. Right? Because for the mutual information you need a two-dimensional probability density function that we just saw, but the Kullback-Leibler divergence just need one-dimensional PDFs, P and Q. Right? Here we just look at the two separate PDFs of channel 1 and channel 2, and that's much easier to compute than a two-dimensional PDF. And then the Kullback-Leibler divergence is defined by this formula here. And you can see it's not symmetric, because here we have P and then this is this log, so depending on if you have P here or Q, we get different results. So that also means the ordering of P and Q matters. But the good thing is the minimum stays the same. So the minimum of D, P and Q is the same as D, Q and P, even though it's not symmetric around this minimum. Yeah, and in Python it's already implemented as part of the package SciPy stats entropy. And for instance, we can assume that Q as a Gaussian distribution with variance 1, and we want to measure how different our distribution P is from this Gaussian distribution Q. Yeah, and we can assume variance 1 since we normalize the signal to its power in the widening step. So it's already having power 1. And then we then sum the divergence of the two channels to the Gaussian distribution. So for each channel we measure the distance to the Gaussian distribution and we maximize this distance. This is a measure that can then be maximized using an optimization procedure. For instance, using the package SciPy optimize. And the resulting mutual PDF can be seen in this following plot. So here we maximized the non-Gaussianity. And indeed, now we can see the PDFs aligned with the axis. Right? So this is basically the two-dimensional PDF that we can now see, and it's now aligned with the axis. So now we can say that this is independent, not just uncorrelated, but now it's independent. Yeah, so here we see that the new structure becomes indeed aligned with plot axis, and this alignment is also what we see if we assume that this PDF is separable, which means it can be written as a multiplication of two one-dimensional functions. So here we have the PDF, the two-dimensional PDF of channel 1 and channel 2. So this is what we here see, right? And this can be written as the PDF of just channel 1 times the PDF of just channel 2, right? So if we have this equality, if it can be written separately as the product of those two one-dimensional products, then it must align with those axes. Otherwise, if there's some diagonal structure, there would be some dependence. Yeah, and that leads us to the Bayes theorem, another information theoretic important theorem. So according to Bayes theorem, that means that channel 1 and channel 2 are statistically independent. So if you can write the probability of two values as probability of value 1 times probability of value 2, then they are statistically independent. So basically the knowledge of the other channel doesn't give us any additional information. So hence these are now independent channel signals. We can now also listen to the resulting signals using this little example, this ICA separation. So which I want to show you first. Copy. Going to my terminal window. ls.py. Let's see if it's there. Yes. So gedit, paste, and here it is. So first I import all the necessary libraries. Here I define a play sound function which plays audio at a given sampling rate and a given number of channels, mono or stereo, so that this is 1 or 2. And here it uses the sound card to play back a given array of samples. Here we define the rotation matrix with a given angle alpha. So here you can see it constructs this rotation matrix R, cosine, minus sine, sine, cosine. Here we define an entropy similarity given alpha and some x. So x contains two signals. X is an array, two-dimensional array, and here you can see it computes the matrix product between x and this rotation matrix R, right? And that's the result x prime. And then here it computes the two histograms of the resulting signals. So this is basically doing the rotation on our signal, and then it computes the histograms. And after computing the histograms, here it computes the similarity using the entropy function of those two histograms. And then it returns the similarity measure. Yeah, so this is the mutual entropy between those two. Then we have, the mutual entropy is another measure of measuring the mutual information. Yeah, so here we have then the main loop. So we read in our stereo file. So this is stereo and contains contains an instrument and a singing voice, I think. And then here we have the scatter plot of the stereo, and it will plot the plot that we already saw. And here it makes an announcement. eSpeak tells you what you will listen to. So first plays back channel 0 and using play sound, and then channel 1. So here you have the stereo sound, and you can listen to the two channels separately. Yeah. Then here it makes an artificial mix. So it takes the sources, multiplies it by this mixing matrix, and this is the new X, which now contains the mixed sources, and then it plots the scatter plot of the mixes. So basically we start here with separated tracks, and then we mix them, and then the goal is to unmix them using the independent component analysis. So in the next step here, we subtract the mean, basically remove possible direct current from the mix. Sometimes that happens in recordings, and it would be just disturbing here. So we remove it. It's not audible, so it doesn't really change anything. And then here we compute our AXX matrix, the autocorrelation matrix for X. And here we compute the eigenvalues. So here we take our AXX, and Eig is the eigen vector and eigenvalue computation of Python. So here you can see it. I import from NumPy, I import linalg as LA. So this in the library linalg, there's this function Eig. So going back, we have it here you go. So this computes the eigenvalues and the eigenvectors. So here lambda contains the eigenvalues and T is now containing the eigenvectors. Right. So this is now our matrix T, our KLT matrix. And here now we perform the KLT. So you can see actually the computation of T is really simple. It's just this one line here. And then we apply the KLT matrix to our signals X using this dot function. So this is a matrix multiplication. And then again we plot the scatter plot after applying the KLT. So this is plotted. And here we can listen to them. So this is the interesting part. So this is before whitening. So here we will listen to one strong and one very weak signal. And then here we do the whitening. Normalize the decorrelated mixes to their power. So here we use square root of lambda because lambda tells us the power for each of those channels. So we just take the square root. We don't need to compute the power because we already have it. And then we have the whitened version. So now we plot it again, scatter plot, and we can listen to it, the decorrelated and whitened mixes. Right. And then we will hear that they now have the equal power, but they will still be mixed. And now we apply or we find a rotation angle which maximizes the entropy based on the entropy based similarity. Maximizes the entropy based differences, it should be. Minimized similarity. This minimizes mutual entropy. Yeah, so first we simply plot this similarity value, this entropy similarity, for different angles. So I am taking 100 angle steps. I divide the angle value range from 0 to 180 into 100 steps and plot the resulting similarity value. Right, and we want to take the one where we have the least similarity. So here you can then see it in this plot, and you can actually see where the similarity becomes minimum. And then I do the actual optimization, the numerical optimization. So here we could actually pick the angle which minimizes the similarity by just visual inspection. But usually you don't want to do it, so usually you want to do the numerical optimization, and this finds this angle automatically. So here again it takes this function entropy similarity. It goes from 0 to 180 in this range, has this additional argument x. X contains our signals, and this is the stopping criterion, and this is the maximum number of iterations which it uses. Yeah, and then it prints the angle which minimizes the similarity. Right, and then we apply it. So here we multiply our x with this rotation matrix with obtained minimized angle, and then we plot again the scatter plot and finally listen to the result, which is now hopefully completely separated. Okay. So yeah, I hope that shows you how this algorithm works. So actually it's all about correlations, computing correlations and computing the eigen values and eigenvectors, and finally minimizing the mutual entropy by applying a rotation matrix. So let me try it. So I'm taking Python 3. Yeah, so here is the original, which is not yet mixed. So this is how it looks like when you have uncorrelated signals. So they are nicely aligned with the axis again, right? So this is before we mix it.
The original source is channel 0.
Too soft.
Channel 1.
And the time.
So you could hear one channel is the guitar, the other channel is the singing voice. And even though they play the same melody, their signals are completely independent. So now we mixed them, the two, with my artificial mixing matrix. So this is what you would observe with those two stereo microphones at the same position, directed in different directions. So basically I now simulated this stereo microphone pickup here. So this is what you usually get at the output of those microphones. Strong correlations.
The mixed source is stereo.
So now mixed.
And the time.
So this is now the stereo mix. And this is now the scatter plot of the mixes after applying the KLT. So now you can see again it's nicely aligned with the axis again, but with very different power. And that makes it impossible to see the fine structure here. Right? So the fine power, the power differences obscures the dependencies between the two channels.
The decorrelated mix is after KLT. Channel 0.
And the time.
Channel 1.
And the time.
Yeah, so here you could actually hear that the first one sounded very soft, but also contained both the guitar and the singing voice. And the second one was much louder, but again it contained both the guitar and the singing voice. So it was not really unmixed, unfortunately. So this basically shows the drawbacks of the KLT. So here one of the assumptions of the KLT, meaning that we have Gaussian distributed subband signals, is violated here, right? And that's why the KLT is not really working in this case. So we have a nice solution, but this nice solution is not really working. That's why we need additional steps now. So now we have this whitened mix. So you can see now it's same size on each axis, and you can also clearly see this diagonal structures, right? There's all those dependencies between the two channels, which are now obvious. So now we need to rotate it using a rotation matrix applied to the two channels.
The decorrelated whitened mix is channel 0.
And the time.
Channel 1.
And the time.
Yeah, so you could clearly hear they sound pretty much the same, right? So now I tried different angles. So here you can see those angles, right? So I'm going from 0, here angle 0, up to 180 degrees, and this is the similarity measure. This is the mutual entropy here. So, and I want to minimize it. So you can see it's negative, so we want to have large numbers, because minimizing means if you have negative numbers, you want to make those numbers large. So here actually it become bigger, smaller and smaller, right? So minus 0.5 or 0.58. So it's always getting smaller and smaller. And around here we get the minimum, minus 2.2. So this looks pretty small. And here on this plot, you also see all those values plotted. And you can see here in this angle, so when you look at the numbers on this part of the screen, you can see it. So we have an x value of 37.7. Yeah, so here 37.8. This is the minimum. And this is actually what we want to use now. This 37.8 leads to the minimum of the similarity. So here we have the minimum mutual entropy. So here this minimum similarity. This is what we want to have here now. There's actually another minimum here. And this might also be a valid minimum because I sampled the angle space quite coarsely, and we see this minimum is really narrow here. And it can be that I jumped over this minimum here. So that's why this minimum might actually be having the same depth as this first minimum. And this is one of the disadvantages of just plotting everything and then sampling the space. I can just overlook a minimum. That's another reason why you wouldn't want to do it like this, right? This can be done to visualize what's happening. I want to find the minimum, but in reality, you always want to apply numerical minimization to find a good minimum here. Okay, so we have one at 37, and here's another one at 127. So let's see. Here's 127 minus 1.1 and 129 also minus 1.1. And maybe in between the two is minus 2, right? We don't know because we didn't try. So then it becomes larger again. It's not so interesting. So let me close. So this is now the numerical optimization. Right, here you can see, here I started, let's see, the numerical optimization. And you can see it iteratively refined this minimum. So here it starts at some alpha, and at this point actually it approaches this alpha at 127, as you can see here. It's getting closer and closer, and it refines it adaptively. So when it finds good values, then it tries to improve those values nearby to get more precise solutions. Right, and it turns out it took this angle at 127.66. So it finds a really precise solution, although it finds here a similarity of minus 1.19. That's interesting. Maybe it's not so good after all. So what we had here at 37, we actually had a minimum similarity of minus 2.2. So this shows you that actually this minimum is indeed not as good, but it is a local minimum which fooled the optimization. This can actually happen because the optimization, this f-min bound, is like most optimizations, is a convex optimization. So that means it assumes there's only one global minimum. But here we saw we have more than one minimum. We have a global minimum and we have a local minimum. And if we have local minima, then global optimizers can find this local minima and get stuck. Here it's happy with this local minimum, and since to each side it becomes worse, it gets stuck. Yeah, so this is also a disadvantage of those optimizers, those numerical optimizers. Usually they are made for convex optimization where there's only one global minimum and they easily get stuck in local minima, which we actually did see. So this is one advantage of having a plot where you simply try everything. You can easily see if it is a local or a global minimum. But the result actually looks quite good. So it's actually not too bad. So here you can see after applying this angle of 127 degrees, it's indeed aligned with the axis. So actually the solution is good enough.
The separated independent signals after ICA. Channel 0. Channel 1.
And the time
Yeah, I would say that is a pretty perfect separation. So it was still a good job. So that worked. So now back to images. This is an example for the KLT for images. We can take an image and read it into Python, as in this code here. Again, I'm using linalg as LA because that's where the Ike function is. I'm using plot, SciPy signal, and I'm using a picture that I took a few years ago in New Jersey, read it in, and then I show it first, and this is the resulting image here that you can see, the original color image. You can see it's from 2009, and this is Maplewood, New Jersey, downtown. So now we can convert it to the two-dimensional luminance component, y. So this is down here. So this is blue, green, and red. Here you get the shape. So we have 2448 pixels times 3264. So this is something like 7 megapixels. And then we can show the y component, which is just a black and white version of it. So now we can construct this matrix X for blocks of size N equals 4. Right? 4 again for simplicity. The dimension of this matrix then is 4 columns and 1,997,568 rows. So this is the total number of pixels here divided by 4, because 4 is our block size. So we get a really tall matrix with almost 2 million rows, but only 4 columns. So we use the command reshape, which reads out a matrix column-wise and puts this in a new matrix with a given dimension. So we can use reshape, y, comma, and then the desired size. Since reshape reads out the values column-wise, we need to transpose the matrices to read out the rows with length 4. So here we can see it. So we take the y. Here this -1 means the number of columns is as many as it needs. And the 4 means we have rows of width 4. So we have 4 columns. And here is the order in which it reads from the matrix. It's C order, which means it's, let's see, row or column wise, I'm not sure. Yeah, so here we can see it. The resulting shape is okay. 2 million rows, 4 columns. Yeah, I think C order means row wise. Yeah. So here we see that it has the correct size. So next we can compute the autocorrelation matrix AXX as X transpose times X, which you can see here. So we take X transpose and X and apply the matrix multiplication, and that's our AXX. And AXX is now much smaller, it's just 4 by 4. Right, it's the correct size. So now we can compute the eigenvectors and eigenvalues. So using linear algebra.eig, so this again computes the matrix T and the eigenvalues lambda. So T now contains the eigenvectors as column vectors. Yeah, and here you can see what's in lambda. That's an array, and this array contains the eigenvalues. And you can see here the first eigenvalues is the largest, and then they become smaller. And this is the way that eig is doing it. It returns the largest eigenvalue first, and also the corresponding eigenvector. And here is T. So here you have the first eigenvector, second eigenvector, and so on. And in the first column you can see you have values which are almost always 0.5. And that's almost identical to the DCT Type 2. Right? In the DCT Type 2, you had exactly 0.5 in the first column, all 0.5s, right? And here you have the next eigenvector, so you have positive values, then to negative values. Here, positive to negative, positive, and then here it changes each time, negative, positive, negative, positive. So this looks like low frequency, medium frequency in the middle two, and highest frequency. So it looks pretty much like a DCT. Yeah, so observe if several of you used different images, they are still resulting in very similar KLT matrices. So that's kind of an interesting observation, because the dependence on the image that you use is not so strong, because it only depends on the statistics of the image, and the statistics of the image for natural images is very similar. So since this is a 4x4 transform matrix, we obtain 4 subband filters with 4 impulse responses, and we can now also plot the 4 impulse responses of our KLT, which I did here. Right, so here I'm opening a plot window and having 4 subplots and plot the different impulse responses. So here I'm plotting the columns flipped. So remember, a flipped column corresponds to the impulse response of the corresponding subband filter. So the result can be seen here. So here you can see the first column, and here you can see indeed it's very close to 0.5. There's very little change, so it's only here in the last digits that it actually changes. So for practical purposes, this is pretty much exactly 0.5. So really similar to the DCT4. Then here you have this slowly changing impulse response going from negative to positive. Then here the next one is changing from positive to negative and back to positive. And then this goes up and down. So it looks like low pass, band pass, high pass. Yeah. Right, so the x-axis is sample and y-axis is the value. So observe that this looks like filters with increasingly higher or lower frequencies. On top is a low-pass filter, below that a bandpass, then another bandpass, and then a high-pass. So simply by starting with a natural image has led us to a subband decomposition where we divide our frequency domain into different subbands. This also has some similarity to the DCT, and this is also why the DCT works. Right, so it's kind of an interesting aha effect. The KLT gives us a familiar subband decomposition like the DCT, and we just started with some natural image. Yeah, and here we can also look at the resulting frequency responses. So instead of plotting the impulse responses, I'm now plotting signal frag Z and plot the dB value of it here in this row, 20 times log base 10. And this is what we obtain. So now indeed, the first subband is the low pass, as we assumed. Then we have the first band pass, not a great band pass, but some band pass, then another band pass here, and then finally a high pass. Right, so a filter bank. So here the x-axis is the frequency and the y-axis is the attenuation here in dB. So in dB. Yeah, observe that the horizontal axis shows the normalized frequencies between 0 and pi. So again, the normalized. So again, we can see that the top figure shows a low-pass filter. Below that we have 2 bandpass filters, and at the bottom a high-pass filter. So now we can verify that the resulting subbands for the rows are indeed uncorrelated or orthogonal to each other. And we compute the row subbands with our KLT. So here now we apply this obtained T to our matrix X, which contains the row snippets of our image. And then we get the resulting subbands, right? YR are the resulting subbands for the rows. So it has a corresponding shape. We have almost 2 million rows and 4 columns. And those 4 columns shall now be uncorrelated. Their cross correlation for lag 0 should be 0. Yeah, so each column YR represents a subbands. And now we have 4 subbands. So now we can compute the correlations between the subbands by simply transposing YR and then matrix multiplied with YR using the dot function again. And this is what we see. So, do we have a diagonal matrix now? We have to look closer. So on the diagonal, we have huge values because that's the total energy in each subband, right? And then we have the cross correlation values, and relatively they are tiny, right? So if you start here with plus 11 and go down to minus 4, you have 15 orders of magnitudes. So there's a factor of 10 to the 15th between the two. And we know that Python has an accuracy of about 10 to the minus 16. So this actually fits to the accuracy, the computation accuracy of Python. So we can assume that those relatively small values here on the off diagonals are actually rounding errors, right? And they are, in reality, they are all zeros, but they appear as non-zero because they are rounding errors, right? So here we can see that the diagonal elements are of significant size, the autocorrelations of the subbands, and the off-diagonal elements are an insignificant size, the cross-correlation. For all practical purposes, they can be neglected. This can also be seen by looking at the ratio of the larger and smaller values. We have a ratio of about 10 to the 11 divided by 10 to the minus 5 is 10 to the 16th. And this is roughly the computational accuracy of Python and corresponds to 160 dB in power. So that's usually much more than we need in our signal processing or compression. Yeah, since autocorrelation corresponds to a power. This is much more than the attenuation of our filters and hence can be neglected. This means the subbands are indeed uncorrelated or orthogonal to each other, and the KLT indeed works, at least for lag 0. Next, we still need to compute the KLT for the columns, right? So basically we can now do the same thing, but just transpose Y, right? So you can just take the same code. I just copy and pasted the same code, but now start with the YT instead of the Y transpose instead of the Y, right? And then you get the T for the columns. So here T for the columns, here the eigenvalues for the columns, and here is the KLT for the columns. So again, here in the first column you can see it's almost identical, right? Here first is again almost precisely 0.5, and then the rest also looks very similar. So here we have it as comparison for the rows, the KLT for the rows. Let's see if I can get it on one screen here. Not quite. So let's take this number here, 0.500428. And here 0.50049. So instead of 48 we have 49, right? Well, 428, and here we have 49. So like 1, 2, 3, 4 digits after the decimal point is identical. So that's pretty good. So here those 5 digits after the decimal point. So for all practical purposes, this KLT for the rows is identical to the KLT for the columns. Yeah, so we can see that the KLTs for the rows and the columns are almost identical for this picture. The slight differences or similarities can also be seen from the correlation matrices for the rows and columns. So here you can see the correlation matrices here for the rows, here for the columns. And also those numbers here are very similar. Here you have 3.58, 3.59. Here you have 3.57, also 3.57. So the statistics are very similar, and that's why you get very similar KLTs. Yeah, to apply these KLTs to transform, an image, we first divide it into blocks B of size 4 by 4 in this case, and then transform each block with a KLT for the columns and for the rows T. So the columns TC comes from the left hand side, and for the rows T from the right hand side. So here is the result. So you take each block B and multiply it from the right hand side with the T for the rows, and from the left hand side we take the transpose of the KLT for the columns. And in the decoder we simply apply the inverse. Right? We take the matrix inverse to obtain the original B back. Yeah, since we know that the KLT matrix consists of the eigenvectors of a symmetric matrix, our correlation matrix, we know that these eigenvectors are orthogonal to each other, and hence the inverse is identical to the transpose, as we can see trying out. So here we have the inverse of our KLT matrix T minus T transpose, and we see it's indeed identical except for rounding errors again. Right? So that shows that our eigenvectors are indeed orthogonal. Yeah, so here we see the differences between the inverse and the transpose is 0 up to the computational accuracy of Python. Hence we can replace the inversion with a transposition, which is much simpler to compute. Right? So in the decoder, this is what you would do. Yeah. So here, for instance, you have the inverse and the transpose, and that just leaves you with a matrix TC. Here you would have, for the rows, you would have the inverse, that leaves you with the transpose. Yeah, and we saw we have the similarity to the discrete cosine transform, so that's why instead of a KLT, usually a DCT is used. If we look at the DCT transform matrix, we can see that it has some similarity to the KLT of usual natural images. This means that the DCT gives us similar compression performance as the KLT, but it has fixed matrix elements which can be standardized, and it has a fast implementation. For those reasons, it is usually adopted in video coding standards. There are actually several types of the DCT, and the most commonly used for image and video coding is the so-called DCT Type 2, as I mentioned. It is defined with this transform as this. Right, so here we have now the cosine terms, we have this n plus 0.5, and k has nothing plus, and this is the definition for the type 2, this type of cosine. So here we see this pi over n, which all cosine transforms have. And then here this index lowercase n goes from 0 to large capital N minus 1. So this is the block size. And here we have some normalization factor, which basically makes it unit length for the matrix. So matrix times matrix transpose, that is one identity. And this CK is a factor which just differs for channel number 0, subband 0. For subband 0, it's square root of 0.5, and all the other subbands, it's 1. Right, again, to make it orthonormal. So here again, K runs from 0 to capital N minus 1. Yeah, K is the frequency index. And both run from 0 to capital N minus 1. So that we get a square transform matrix T. So this is then the transform matrix with the entries n, k. So we can compute now this matrix T from this formula. So this formula is then the same for the encoder and decoder, and we don't need to transmit it as site information. Yeah, and here this shift of 0.5 in the space index and not in the frequency index is typical for the DCT of type 2. And this is the most commonly used type in video and image coding, because the higher subbands have zeros in their frequency response at frequency DC, what we also observed at the KLT. And this is important because this suppresses the high DC energy of usual pictures for the higher subbands sufficiently. So we don't want to have any high energy from the lowest subband to spread into the weaker higher subbands, because that would then dominate the energy there, and again we would lose coding efficiency. Yeah, so this is important for good coding gain. In this way we don't have to encode the DC energy in higher subbands again. And the DCT matrix is designed such that it is orthonormal, which means its inverse is identical to its transpose. So very practical. This automatically also means that it is invertible by using its transpose, which is important for the decoder where we would like to reconstruct the original blocks of our image. Observe that we can decompose the image into smaller blocks to obtain a time or space and frequency decomposition. So we have both frequency inside the blocks and space for the position of the blocks. We reduce the spatial resolution to the size of our blocks, but for that we obtain frequency information within each block. We can say in which block a certain frequency component appears. And in this way we obtain a different representation of our image, where we can take advantage of the frequency information, for instance, to use that most energy is expected at low frequencies, or that the eye has the highest sensitivity also at the lower frequencies. Hence we will put most of our bits into representing the low frequencies and very few bits into the higher frequencies. So here's a Python example for the DCT. We assume a number of subbands of, again, n equals 4, and we generate our transform matrix T, which you can see here. So we initialize with zeros, and then we have those two for loops where we just plug in our cosine formula here that we just saw. And then for subband number 0 we have this additional factor of square root of 0.5, right? And this leaves us to this transform matrix. So again we see here 0.5 for the first column. So this is exactly what we just observed for the KLT. And then again we have positive, positive, negative, negative, plus, minus, minus, plus, and then plus, minus, plus, minus. So it's very similar to the KLT. So we check if our computed matrix is indeed orthonormal, as it should be, by checking if T times T transpose is identity. So here we do it. We multiply the two, T by T transpose, and indeed on the diagonal we get 1s, and on the off diagonal we get numbers on the order of 10 to the minus 16, which means it's just rounding errors, and in reality it's 0. So that works. Indeed, the identity matrix, and practically zeros on the off diagonals. So now we can also plot the impulse responses and each frequency response of its 4 equivalent filters, as we did for the KLT. Right, so here again subplots, and here is the result. So now we have the first impulse response of subband number 0, really constant, 0.5. Then here the next subband, and the high pass up, down. And we can now also compare it to the KLT here. So again, this was the KLT, and it looks almost the same, except for some slight changes. Right, when you compare it here, it's almost exactly 0.5, but slight deviations here. Here we have a constant rise. Compare that to our DCT Type 2. So it rises up. Same thing, it rises up. Then the next goes from positive to negative up to positive, and then we have those final wiggles. So going back down. So here positive to positive, and here those wiggles. So it's almost exactly the same. And this is quite interesting because the KLT was derived from statistics of our natural image, and the DCT comes from a formula, right? Quite different origins. So now we can plot the equivalent filters of the DCT with this code here. And here's the result. So again, first subband, a low pass filter. Next subband, a band pass, not a great band pass, but a band pass. Then a somewhat higher band pass. And here we have the high pass. And you can see here the three higher subbands all have zeros at frequency 0. So they have an extremely high attenuation at DC at frequency 0, each of those. And that's important for coding efficiency, because at frequency 0 we will have most energy, and we want to appear this high energy only at subband number 0, but not at the higher subbands. Yeah. So almost the same subbands of a filter bank with low pass on top, below that band pass filter with increasing center frequency, and then a high pass. Also observe that except for the low pass filter, the higher filters have all zeros. The transfer function is 0 in the linear scale, meaning infinite attenuation or minus infinity in the dB scale at frequency 0, meaning DC. And this is important because natural images often have a lot of energy around DC, and this keeps it out of the higher filters to save bits, as I just said. And again, this is quite similar to the KLT. So again, here are the filters of the KLT. They look slightly different, but not so much. So you can actually see a slight difference at frequency 0. So this comes a little bit closer to 0 here, and this is actually having a dip a little bit aside from frequency 0, which is kind of interesting. It's not quite the same. Here again it goes down, but it seems to be a little bit closer to frequency 0. So it seems that DCT type 4 is doing a better job suppressing DC. Yeah, observe that the DCT makes no difference for rows and columns. Hence, it is the same for both sides. We make no difference between TC and T in this case. To transform our image blocks, we just multiply the same type of matrix from each side, and in the decoder, we just use the inverse or transpose. Yeah, and finally, we also have the Walsh-Hadamard transform. This is another interesting transform for images and video. And that is the so-called Walsh-Hadamard transform, as the name says. And this is defined by this simple matrix here. So we start with a 2x2 matrix. And you can see here, first column is a low-pass filter, and the next column is the high-pass filter. Here we have the change in the sign. Here we have the constant value, and then we have a factor to make it orthonormal. And then we obtain higher order of this transform by this recursion, right? HM consists of 4 of those HM minus 1, which we plug in here. And then we have another normalization for orthonormality. So in the end, this matrix always consists of only plus minus 1s, right? Which means no multiplications, only sign changes. And the factors with square root of 2 are for making the transform orthonormal, but they are not necessarily needed for an implementation, right? We can always do it in the end. This makes it very computationally efficient. But since the matrix entries here are now less similar to the KLT, the compression performance is usually not as high as with a DCT, at least for usual images. Remember, the KLT depends on the image, and there might be, for instance, artificial images where the KLT becomes more similar to a Walsh-Hadamard transform, right? Observe that it also has similarity to a DCT where you only keep the signs, so the sign of this transform. So you could also obtain this Walsh-Hadamard transform by just applying the sign function to the DCT transform matrix. Okay, so That's it for today. Thank you for your attention, and then see you next time.